Hello everyone. First of all, I would like to thank you for giving us the opportunity to disclose the results of our research and share them with all the participants. Today, I'll be privileged to present this work that was carried out at the Faculty of Sciences Benamsik, based in Casablanca, Morocco, in collaboration with Dibra University, located in India, that provided us with some of the necessary resources during this research. It's an overall research incorporating several computational methods, notably the quasar study, the ADMET properties investigation, molecular docking, and molecular dynamics simulation, towards designing a potential new HIV-1 protease inhibitor. This work was conducted under the supervision of Professor Said Bilawad. First of all, there is a brief introduction displaying the main purpose of this research. Secondly, the material and the methods adopted should be mentioned. Furthermore, the results must be discussed, followed by ADMET properties investigation, then the molecular docking study as well as the molecular dynamics simulation. And finally, I'll sum up the main results in a brief conclusion. The virus we're targeting here is the human immunodeficiency virus, which is the HIV, one of the most challenging viruses in medicine that causes serious complications related to the human health. To overcome this issue, drugs were synthesized and used in combinations to treat the HIV infection, forming what we call the highly active antiretroviral therapy, HAART. But the rapid emergence of multi-drug resistant strains of HIV-1 protease as well as the poor oral bioavailability and side effects had severely limited long-term treatment options. Here comes the necessity of designing new efficient compounds. A series of compounds synthesized and evaluated in a previous work were used in the current research. One of the main purposes of this study is to develop a quantitative structure-activity relationship model able to relate the structure feeders, which mean descriptors that characterize the compounds, to the biological activity of these drug candidates against HIV-1 protease. To do so, various computational methods were performed using variable softwares, notably Gaussian, XLStat, MATLAB, ChemOffice, Autodoc MGL tools, GROMACS, etc. To carry out the research, we had to select a series of compounds. Eventually, we used a series of 33 elements evaluated as highly active against HIV-1 protease in a previous work. Each compound has an inhibitory effect on the activity of the HIV-1 protease. In the current study, we converted the biological activity to the negative logarithm using the following equation. Furthermore, several softwares were used in order to compute various descriptors such as Gaussian, Chem3D, ChemSketch, and Marvin Sketch, but only some descriptors that are correlated with the activity will be used in order to minimize the size of the data representation space. The other descriptors that are not correlated with the activity or that are correlated with each other will be eliminated because they carry the same amount of information. The computed descriptors must be the object of the descriptive analysis. On the one hand, eliminate the correlated descriptors using principal component analysis, and on the other hand, split the dataset into training set and test set using dataset clustering. The first one will be used to generate the model, while the second one is going to be used to validate it. Afterwards, the model was generated using XLStat, a statistical software that is used as an add-on for Excel. The best model was selected based on its statistical parameters that must be optimal. Unfortunately, the statistical parameters aren't enough to promote the model. It must be validated in two steps: the internal validation using the leave one out cross-validation method and the external validation using the test set that we mentioned previously. Obtained coefficients seem to be good enough to consider the model as robust and not a result of chance. Unfortunately, even after the validation step, the model can be used to predict some other active drugs since the applicability domain is not determined. Therefore, we used MATLAB to determine the applicability domain that shows no outliers in our datasets. Now, we can jump to the prediction step towards designing new effective drugs. 24 compounds were designed based on the most active elements in the series of the 33 compounds. They represented the object of structural modifications in order to design new molecules. Among the 24 compounds, only one compound, which is the 16th, has a leverage value equal to 0.43, lower than the Warning leverage, which is 0.45, and a biological activity higher than the known ones, which is equal to 1.58. Right after the designing of the brand new drug comes the step to predict its druggability capacity. So, ADMET properties or ADMET parameters, as well as the physicochemical properties of the proposed compound, were computed online using SwissADM and PKCSM servers. On the one hand, regarding Lipinski's rule, the drug likeness of the proposed compound was verified with only one violation, which is the molecular weight, which is higher than 500, as shown in the table. So, based on these results, these computed properties, we can say that the proposed compound is sufficiently absorbable via oral route, especially regarding its bioavailability score, which is higher than 0.5. It is equal to 0.55. Besides, ADMET properties related to the brand new drug that stand for absorption, distribution, metabolism, excretion, and toxicity gave us some promising values with no threat on human health. Then comes the molecular docking study step. Molecular docking is a method which analyzes the conformation and orientation of molecules into the binding site of a macromolecular target, which is the protein. In our case, we have the HIV-1 protease, and the ligand, which is the small molecule, is the new drug that we just designed and we just computed its parameters. Searching algorithms generate possible poses which are ranked by scoring functions. In our case, the scoring functions will be based on the binding affinity. A comparative study will be conducted using two types of the protease, not only the wild type but also the mutant type of the HIV-1 protease. Both will be docked to the potential drug candidate in the binding site location. Searching algorithms generate possible poses, which are 9, that will be ranked using scoring functions based on the affinity value. As you can see, the first pose is the best for both complex compounds. For the complex compounds incorporating the wild type, it has an affinity value lower than the affinity value of the mutant type. Why? We'll see the answer in the upcoming slides. As the molecular docking results show, the complex compound involving the wild type is more stable than the other complex involving the mutant type. We can explain this by the interaction types that are various for the wild type as compared to the mutant type. As I previously mentioned, in the current work, we conducted a comparative study using an FDA drug, which is lopinavir, based on the optimal results of the affinity values obtained for both types of the HIV-1 protease as compared to the other drugs. So, minus 7.5 kilocalories per mole is the affinity value for the wild-type protease compound, while minus 7.7 kilocalories per mole for the mutant-type protease compound. Comparing the four complex compounds, we can say that the wild-type protease shows similar affinity values whether docked to the new drug or to lopinavir. In contrast, for the mutant type, the compound with lopinavir is showing higher stability than the one docked to the new drug. These differences can be explained based on the interaction types. More the compound is displaying various interactions, more it is showing higher stability. Here comes the molecular dynamics simulation step. Molecular dynamics simulation is the greatest tool to visualize the motion of particles at the atomic level and to investigate the stability of these particles. To investigate the stability of all compounds, basically the complex ones involving both wild type and mutant type, we performed the molecular dynamics simulation that allowed us to investigate the stability of these complex compounds through several techniques, namely root mean square deviation, root mean square fluctuation, and the radius of gyration, as well as the number of hydrogen bonds, which is not mentioned here. So here we have the root mean square deviation plots for all compounds the full complex compounds as well as the native proteins. As the root mean square deviation plots display, the native proteins show interesting stability within 50 nanoseconds, especially for the wild type that maintained its stability until 60 nanoseconds of the simulation time. Regarding the root mean square deviation plots for the two complexes, wild type lopinavir and wild type new drug, it is highly clear that these compounds are showing slightly higher fluctuations than the native protein, especially for the wild type lopinavir. As for the compound mutant type new drug, it is showing in average a higher stability as compared to the mutant type lopinavir that displays more fluctuations as compared to both native protein and mutant type new drug. While these plots display the root mean square fluctuation for all compounds as well. The root mean square fluctuation plots for the mutant type and the wild type as well as the complex compounds during the period of simulation, which is 100 nanoseconds. In both figures, whether considering the wild type or the mutant type, the compounds are showing highly similar fluctuations, except for the complex referred to by mutant type new drug that shows less similarity for the first nanoseconds of the simulation process, that we might ignore and conclude that the complexation has no important influence on the flexibility of the proteins. Regarding the radius of gyration, it is an interesting parameter as well to investigate the motion of a protein. It describes the compactness of the protein during the simulation time. Based on the plots, we can assume that the compactness of a compound is eventually affected by complexation. In other words, ligands can modify the compactness of the native proteins, whether increase it or decrease it. It depends on the situation. Here we come to the number of hydrogen bonds. As we already know, the hydrogen bonds play an important role in the stability of the complex compound. So here we have the simulation results showing the number of hydrogen bonds during the simulation period of complex compounds containing mutant type and wild type. Here we have only the complex compounds. And the plots are showing, the graphs are showing how many hydrogen bonds are present in between the ligand and the protein, whether it is the mutant protein or the wild type protein. The graphs show the number of hydrogen bonds present in the complex compounds, which is either 2 or 3 for the mutant type or 3 to 4 for the wild type. More there is hydrogen bonds, more the complex compound is stable. In the conclusion, on the slide, I tried to gather all the findings, but I'm not going to talk about the findings, but I'm going to talk mostly about the benefit of the computational chemistry. So as a conclusion, we cannot deny the benefit of computational studies in the discovery of new efficient drugs. Instead of jumping directly into the phase of production in laboratories, it is always recommended to do the simulation previously to visualize the final result, and then decide whether to go forward or leave it for lack in some of the required properties. And finally, I would like to thank you all for your precious time as well as for this priceless opportunity to share our findings with everyone.